Now we're going to look at another tool that can help us determine or find the real zeros of a polynomial function, and that is called the rational zero theorem. Now, the rational zero theorem would state that the universe, I guess you might say, or the set of numbers that might represent the real zeros of a polynomial function can be expressed by all the factors of the constant over all the factors of the lead coefficient. And we call this P over Q, where P represents all the factors of the constant in the polynomial equation, and Q represents all the factors of the lead coefficient of that equation. And so here we got 3x cubed minus 4x plus 10. And so we're trying to narrow down a universe of what could possibly be the real zeros of this function, absent graphing it, of course. And so I start here with all the factors of 10, and I have to include plus or minus, because even to get to positive 10, I could have -2 and -5, right? Or some other real zero. So all the factors of the constant in this case would be plus or minus 1, plus or minus 2, plus or minus 5, and lastly, plus or minus 10. Can you think of any other factors of 10? I don't think so. And then I've got that over plus or minus 1 and plus or minus 3, because there's only two factors of 3, 1 and 3. All right, now I perform the operation. Now, divide everything by 1, well, it's just going to be plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, but I also am going to divide by plus or minus 3. So let's see, what are all our factors? Well, let's just start with the obvious. So I got plus or minus 1, plus or minus 2, plus or minus 3. No, it's not 3, 5, excuse me, 5, jumping ahead, plus or minus 5, plus or minus 10. And then we would also include plus or minus 1/3, plus or minus 2/3, plus or minus 5/3, and then finally plus or minus 10/3. And so that is our universe of what could possibly be real zeros into this function. And we could start testing those using synthetic substitution. See if we get a zero remainder. Remember our zero remainder theorem, and determine the real zeros of that function. Now let's go ahead and look at another function, and we're going to identify all the possible zeros. All right, well, this time we caught a bit of a break because our lead coefficient is 1. So that's going to make this a little bit easier. But again, we're looking at P over Q, all the factors of the constant, over all the factors of the lead coefficient. So now I'm dealing here with plus or minus, with 24. Well, let's see, I got plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. Let's see, why do I say that? Okay, and then plus or minus, well, let's see. The reason why we would have plus or minus 4 is 4 times 6, so we got plus or minus 6. 3 times 8 is 24, so I got plus or minus 8. 2 times 12 is 24, so I got plus or minus 12. And 1 times 24 is 24, so plus or minus 24. Let's see, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, 8, 12, 24. That's it. Now, all of that would be technically over plus or minus 1. But, of course, any of those numbers divided by plus or minus 1 are just going to equal itself. And so all the possible real zeros of this function, h of x equals x cubed plus x squared plus 24, is contained right there. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. Identifying all the possible real zeros using the rational zero theorem, which states that all the possible real zeros of any function can be found within a set of numbers that would equal all the factors of the constant divided by all the factors of the lead coefficient.